This chapter is about what happens to energy of chemicals during a physical or chemical change. Now, all chemicals have a certain amount of energy stored in them. This is called chemical potential energy. Now, when a physical or chemical change takes place, the chemicals either give out energy to the surroundings or take in energy from the surroundings. If energy is given out to the surroundings, it is called exothermic. If energy is taken in from the surroundings, it is called endothermic. Let's start with what happens to energy of chemicals during an exothermic reaction. At first, the reactants are at a certain energy level. Since the reactants give out energy to the surroundings, that means the products formed have a lower energy than before. And this is shown by the energy level diagram here. So, reactants have higher energy, products have lower energy. So there's an energy difference now. This energy given out is in the form of heat, and the surroundings will gain heat. A simple example is when you burn a fuel. Burning gives out heat. So if you stand near a fire, you can detect the heat. This heat received by the surroundings can be detected by a rise in temperature. What about an endothermic change? In an endothermic change, again, the reactants are at a certain energy level at the start. But the reactants take in energy from the surroundings. So that means the products formed have a higher energy than before. A good example is photosynthesis, in which green plants absorb or take in sunlight energy to combine carbon dioxide and water to form glucose. So the final product, glucose, has higher energy than the reactants, carbon dioxide and water. So this energy level diagram shows that for an endothermic reaction, the energy of the products is always higher than that of the reactants. So this energy taken in is stored in the molecules of the products, in this case, glucose. And what happens to the temperature of the surroundings? So the temperature of the surroundings will fall or will decrease because the surroundings are losing heat. So some of the sunlight energy, right, is used up or taken in by the carbon dioxide and water to form glucose. Here is a common example of an exothermic reaction, the dissolving of an alkali such as sodium hydroxide in water. Before you add the sodium hydroxide to water, the water is at room temperature, which in this case is 28 degrees Celsius. After adding sodium hydroxide and stirring, the sodium hydroxide dissolves, a reaction takes place, and the reactants give out heat to the surroundings. What are the immediate surroundings here? The immediate surroundings are the container and the thermometer, which is not shown here. So the container and the thermometer become hot. So if you have a thermometer inside, the thermometer will show a rise in temperature. In this case, this example shows temperature rising from 28 degrees Celsius to 34 degrees Celsius. Let's track how temperature changes when sodium hydroxide dissolves in water. Now, before sodium hydroxide is added, the water is at room temperature. After sodium hydroxide is added, heat is given out. This heat is picked up by the thermometer on the container. So, there will be a rise in temperature on the thermometer. The temperature will not rise forever. It will reach a maximum when all the sodium hydroxide is dissolved. But after reaching the maximum, the temperature will fall again when the hot cup and the thermometer lose heat to the surrounding air through physical processes such as conduction, convection, radiation. The temperature then drops back to room temperature at the most. Compare this to a cup of hot water. It will not remain hot forever, but it will lose heat to the surrounding air until room temperature is reached. Here is an example of an endothermic change. When ammonium salts or nitrate salts dissolve in water, an endothermic change takes place. The water is at room temperature before the ammonium salt is added. When ammonium chloride is added, the reactants absorb heat from the immediate surroundings, which are the container and the thermometer, which is not shown in this diagram. This energy absorbed by the reactants is changed into chemical potential energy and stored in the ammonium chloride solution. Now, as a thermometer can only detect heat energy, the energy absorbed does not show as a rise in temperature because the energy absorbed is stored in the ammonium chloride solution as chemical potential energy. However, since the container and thermometer lose heat to the reactants, the container and the thermometer become cold and the thermometer will show a fall in temperature. This slide tracks what happens to the thermometer during an endothermic change. At the start, the water is at room temperature. In this example, it is 28 degrees Celsius. When ammonium chloride starts to dissolve, it absorbs heat from the thermometer and the cup and the container. So the thermometer will fall until it reaches a minimum. Now it reaches a minimum when all the ammonium chloride has dissolved. So the solution, which is now cold, will then absorb heat again from the air by conduction or radiation until it reaches room temperature again. Compare this to a cup of ice water. It will not remain cold forever. As it is colder than the surrounding air, it will absorb heat from the air until room temperature is reached. Changes of state are not chemical reactions, but still involve energy changes. Freezing, for example, is exothermic. Example, when water changes to ice. We can use a kinetic particle theory to explain this. Liquid particles have higher energy than solid particles. So, for a liquid to change to solid, it must give up this so-called excess energy. As the liquid particles lose energy, they move more slowly and are gradually attracted to one another until the particles become so close together in fixed positions and the solid is formed. Condensation is also exothermic. For example, when steam changes to water. Particles in steam are higher in energy than particles in water. So, for steam to change to water, this so-called excess heat must be given out. As particles in steam lose heat, they move more slowly and start to attract each other again. When particles move close enough together and can only slide over one another, water is formed. Some changes of state are endothermic. An example is melting. During the melting of ice, heat energy is absorbed by particles in the ice. So, the ice particles vibrate faster and move further apart from each other. Now, ice then changes in state to become water. This explains why your tongue feels cool when you lick an ice cream. The ice cream absorbs heat energy from your tongue, so your tongue becomes colder. Changes of state such as boiling and evaporation are also endothermic. Liquid particles have lower energy than particles in steam or water vapor. When water boils, it must gain enough heat so that the particles gain enough energy to move randomly at high speeds at the boiling point. Similarly, during evaporation, which can take place at any temperature, liquid particles collide, and some particles gain enough energy to move to the surface. These particles, which reach the surface, have more energy than the ones below, so have enough energy to pull away from the particles below and escape into the air as water vapor. This slide shows many examples of exothermic changes, but I will just highlight some of them. An obvious example is burning or combustion, because during burning or combustion, heat is given out to the surroundings. Now, an acid-alkali neutralization is also exothermic. So if you mix acid and alkali together, heat is given out, and if there's a thermometer in the container, in the mixture, the temperature will rise. Now, respiration is a reaction which takes place in plant and animal cells. During respiration, glucose is oxidized to release energy, and this energy keeps the body warm. The energy released can be used for movement, for repair of tissues, and so on. Here are some examples of endothermic reactions. One of them is photosynthesis, in which carbon dioxide and water in green plants absorb sunlight energy to form the high energy product called glucose. Now, other reactions that are also endothermic are those which require to absorb heat energy in order to decompose. An example is thermal decomposition of most metal carbonates to form metal oxide and carbon dioxide. So only when you heat the metal carbonate absorbs enough energy and can then decompose. Another example is decomposition of silver salts or silver halides like silver chloride, silver bromide, and so on. Now, when silver halides absorb light energy, they break down into silver metal and the halogen gas. For example, silver chloride breaks down to form silver metal and chlorine gas. Silver bromide breaks down to give silver metal and bromine gas is released. This slide explains why some chemical reactions are endothermic while others are exothermic. Note that this does not apply to changes of state, only for chemical reactions. The theory is that for any chemical reaction to take place, bonds in reactant molecules must first be broken. So for that to happen, reactant molecules must first absorb energy. So bond breaking in reactant molecules is always endothermic. The reactant molecules break into atoms, and these atoms have so much energy that they cannot come together to form new bonds in the products unless they give up some of the energy gained. Then they slow down and move closer together to form new bonds. This means that bond making to form products is always exothermic. This slide explains why a reaction is exothermic. The first part of any reaction is the same. Bonds in reactor molecules must be broken, and so energy is absorbed. So bond breaking is always endothermic. To form the products, some of the energy absorbed must be given out. So bond making is always exothermic. But in an exothermic reaction, more energy is given out to make new bonds compared to energy absorbed to break bonds in reactants. This means the reactants have given out more energy than it absorbed from an external source, such as a fire. So where does this extra energy come from? It comes from the chemicals themselves, of course. So it is like comparing an exothermic reaction to someone who is a big spender. He spends more than he earns. He may earn a certain amount of money, but in this case, it is energy. But he spends more money or more energy than he earns. So where does he get the extra money or energy from? From his savings, of course. Because every set of chemicals has a certain starting energy. So that is the energy saved. But his savings will now dip lower. So this extra energy given out is called enthalpy change, represented by the symbol delta H. Now, since the energy of the products is lower than the energy of the reactants at the beginning, this difference in energy, which comes from the chemicals themselves, right, is given a negative sign. So delta H is negative. This slide shows energy changes taking place on endothermic reaction. The first part of the reaction is the same. Bonds in reactor molecules must first be broken, and so energy is absorbed. So bond breaking is always endothermic. To form the products, some of the energy absorbed must be released. So bond making again is always exothermic. But in an endothermic reaction, less energy is given out to make new bonds compared to energy absorbed to break bonds in reactants. So this means the reactants give out less energy than they absorb from the external source. So the products retain most of the energy absorbed from an external source, such as the sun in photosynthesis. So an endothermic reaction can be compared to someone who is very thrifty. He is a saver. He saves more than he spends. So at the end of everything, his savings will be higher than at the start. So this extra energy retained in the products is called enthalpy change, represented by the symbol delta H or triangle H. Since the energy of the products is higher than that of the reactants, the difference in energy between reactants and products, delta H, is given a positive sign.